Okay, now let's continue what I was telling you about Hertz here and his, and basically what he ended up doing was generating radio waves for the first time. And they came to be called radio waves later, but they're electromagnetic waves of much longer wavelength than visible light is. And but Hertz generated these waves and then showed that they have all the same properties of light. It's just that our eyes don't respond to them because our eyes only respond to really, really short wavelength light. Okay, so I started to tell you exactly how he did this. Now, basically he had a coil of wire and attached through wires to little metal spheres with a gap between them. And in essence, what he does here is he creates a very quickly changing strong magnetic field through this coil, which starts a current flowing, right? I mean, if you put a changing magnetic field through the coil, that's going to induce a current in that coil. So it induces this large current in the coil that then will make one of these, will make these little metal spheres charge up to the point where the field between them is so strong that it causes a spark. And what Hertz found was that by adjusting the size of these little metal spheres and the size and number of turns of this coil, he could get electricity to oscillate back and forth through this system at the frequency that he wanted that would create the kind of wave that he wanted. I mean, he wanted a wave where the wavelength was manageable in the laboratory, and so that he could test all these properties of light, such as interference properties or so on. I mean, if he has little tiny waves, it's not going to be possible for him to see these wave properties easily in the lab. On the other hand, if he has a wavelength that's as big as the United States, that's not going to be good either. So he has to have a wavelength. He has to produce a wavelength of light where he can move his detector around and notice null spots and then maximum spots and so on, so he can actually find the wave. And so he wants a wave that's just a few feet long, the wavelength. And by adjusting this coil and the size of these little spheres in the spark gap, he finds out that he can generate a wave that's just like 2 or 3 feet in wavelength. Okay. Now, I want to show you, just to explain roughly, his procedure is to go through that list of properties of light, basically, that we saw this morning, and show that his waves that he gets when he oscillates a current in this system and gets little sparks to fly back and forth between these little spheres, the waves that come out from that they have all these properties that I told you about. that they can be reflected, they can be refracted, that they're polarized, and so on. Now I mentioned that his detector is another thing a lot like this. It's just a wire loop with a couple little metal spheres and a little gap between them. And when there is an electric field between that gap, then he'll see little sparks. So he can detect the presence of an electric field. So, he starts a current, a strong current, oscillating through this system. And what happens in this system is, like, he'll induce a current. Let's say he induces a current in this direction. This little sphere will charge up positive, and this one will charge up negative, to the point where then you get a spark jumping across. And once the current, once all the positive, it's just like a pendulum, basically, is the way this electric circuit works. The charge will, swing in one direction, and then swing back in the other direction, and then swing through in the other direction. So it's like a pendulum just swinging back and forth, and Hertz will get just a series of sparks across this little gap that then generates these electromagnetic waves of the same frequency. Okay, so, and he can detect those with this little spark gap detector that he can wander around with in his laboratory. So he points this thing at what he figures will serve as a mirror, basically, for these electromagnetic waves. Now, what would you think? What kind of a substance would you think that electromagnetic waves would reflect off of? Sure. Visible light will bounce off a mirror. Turns out that these long wavelength waves bounce much better off of metallic surface. He just used, I believe it was copper, something like a sheet of copper, okay, to bounce these waves off of, and that worked fine. So he shows, though, that he can generate these waves and then detect them with his detector, okay? But then he can, even if he puts something between his, let me draw the same circuit over here. Okay, so here's his EM transmitter. And let's say he put some shield between the transmitter and his detector here. Okay, so he he puts some metal object between his wave generator and his detector, so he's not going to detect anything, right? He's not going to have any sparks here. Well, if he puts his copper mirror up here so that the waves can bounce off and get to his detector, sure enough, now he starts detecting sparks. Okay, so he shows, by means of experiments like this, that these waves do reflect off of metallic surfaces. And they reflect just the way ordinary light does off of mirrors. I mean, they obey the law of reflection, that the angle of incidence equals the angle of reflection. Okay, now, what he wants to test the law of refraction. See if these electromagnetic waves that he's generating will bend going through materials. Well, he makes a prism, okay, a big prism. He's got a now it's not the kind of prism that Newton used a little glass wedge, right? Well, Hertz's waves are bigger, so he needs a bigger prism. So he gets it's still wedge-shaped, but he's got a 1,200-pound slab of asphalt, okay, that's cut in a wedge that he uses as his prism. And sure enough, he finds that these electromagnetic waves bend as they go through it. He can tell that when he puts, he's detecting his waves say at a certain spot over here, and then he puts his big prism in here. So 1,200 pounds of asphalt. And he finds he has to move his detector a certain amount to locate the wave again and get sparks across it. So obviously his asphalt prism has changed the direction of the wave, and he finds he's actually able to calculate the index of refraction of this asphalt prism that he's sending his waves through, and he comes up with well, do you remember what the index of refraction for glass is for visible light? It's about 1.5. Okay, so 1.5 is a sort of standard index of refraction. It's a measure of how the further it is from 1, the more it bends the light. Okay, so he comes up with an index of refraction for his asphalt prism of 1.7. But it's still it obeys this sine law of refraction that that was discovered 250 years earlier by Snell. Okay, now what else did we have? We had, that light, of course, was a wave that has interference properties, right? So, in order to show that these electromagnetic waves can combine and add or subtract when they combine, Hertz does another kind of experiment. He takes, let me see, how best to draw this. He takes two mirrors that he bounces these waves off of. Okay, so one wave is going to this mirror, one wave is going to this mirror, and then they bounce off, and he detects them across the room someplace. So he's got his detector, say, over here. Now, when it's the same distance from each mirror to his detector, okay, then the waves should reinforce one another, right? Because they're going to be adding in phase, okay, because they've each traveled the same distance. But then when he moves the detector so it's a little closer to one than it is to the other, and let's say the wave that's coming from the mirror that's further away has to travel an extra half wavelength, okay, then the two waves are going to add out of phase. They're going to cancel each other. Well, that's exactly what he finds. He finds just this effect, that let's say that his wavelength that he's generating waves with a 1 meter wavelength. Well, and he's bouncing them off these two mirrors. Well, when he's a half meter further away from one of the mirrors than he is from the other, he won't detect anything, because the two waves will be exactly out of phase. When one of them, when the electric field from one is at a maximum, the electric field from the other will be at a minimum, and they'll cancel each other. Okay, so he proves by means of generating, two waves basically that are bouncing off different mirrors, that he can get interference effects just like this. So you can write in your notes. Bouncing the waves, by bouncing the waves off two mirrors, and detecting the combined waves at various distances, he proves that the EM waves interfere or well, I mean, you know what that means when I say interfere. It just means that when they add, they can, they can add or subtract. Okay, so now, how could he test whether they have whether they're polarized, whether these waves are polarized? Any ideas? Neat.
Take those crystals and see if you could block them out.
Yeah, okay. That's what we need. We need something like the crystals. Now, it turns out that the crystals that work for visible light don't work for this much, much longer wavelength light. This light isn't blocked by those crystals, no matter what orientation you put the crystals in. So, but he's already found something, Hertz has, that will block this light. Right? I mean, big sheets of copper. Okay? So what should he do? Let's say he's generating his wave in this by shooting sparks across this little gap. He knows that if he just puts a big sheet of copper here, he will block the wave that's traveling to his detector. Okay, so he can be detecting sparks over here with his little spark gap detector, but if he puts a sheet of copper between him and his transmitter, then he doesn't get any sparks anymore. Well, what if he puts a rather than a sheet of copper, let's say he takes let's say he has a grid, some kind of, I don't know, you can just have like a wooden frame here that he strings copper wire down it. Okay. So rather than a sheet of copper, he's got just a whole bunch of copper wires. Wrapped around a wooden frame. Now, if, let's say the electric field of this wave is oscillating up and down here. Now, if I put if I take this and put it so the copper wires are horizontal. Okay, so they're going into and out of the board. So I'm going to put my, this is Hertz's polarizer. If you orient it so that so the copper wires are horizontal. What do you think is going to happen? Troy?
You won't pick up any sparks.
Oh, so you don't think this oscillation of the E field will get through?
Well, because it's horizontal and that's up and down, so it will.
Yeah, it actually will. Troy's right. If you have it so the copper wires are horizontal here, they're perpendicular to the oscillations of the electric field, then it can't it can't make any current flow in these wires because they're not oriented in the right direction. So this thing won't have any effect on the wave, and the wave will just go right through it. Okay, and then you will observe sparks over here. It's like this thing isn't even there. It's just transparent to this wave. Whereas if you flip it around, and so the copper wires run vertical, well now this electric field oscillation is going to stir up current in those wires, and that's going to, so it's in effect it's going to absorb this wave and not let it through. Troy?
Does he have a detector for magnetic fields too? Or?
No, he just had this spark gap detector. So he's just detecting, I mean, he's creating both an electric field and a magnetic field, of course. But what he's able to detect is just the electric field. Okay, so when the copper wires are oriented in the same direction as the electric field, they will that electric field will create current in those wires, and the Hertz's polarizer will absorb the wave. Whereas if he turns at 90 degrees so that the wires are oriented perpendicular to the electric field, then the electric field just passes right through it. Okay, so he's shown, I mean, first, it's obvious this is a, once he does this, it's obvious this is a transverse wave, and you have polarization just the way that you do with light. Okay. Now, the other thing that Hertz does, and I'm not quite sure exactly how he did this. I couldn't find any details on it. It must have been extraordinarily clever. But he was actually able to measure the, as the current oscillates back and forth through this, this circuit that he's devised, it creates these sparks that fly back and forth between these two little metal spheres. Now, Hertz was able, with a very fast spinning mirror, he was able to figure out the frequency of those sparks. I don't know, that's all my book says, so I can't, I'll try to get some more information on that for you, but it's, somehow he was actually able to measure this frequency of the sparks flying back and forth between these two little metal spheres. And so he knew the frequency of the wave that he was creating. Now, it turned out to be on the order of 100 million cycles per second. Now, he was able to, if you know the frequency of a wave and you know its wavelength, and he could measure the wavelength just by moving his spark gap detector around and seeing where the nulls were and where the maximums were. Okay, so he could, he was able to measure the wavelength and the frequency of these waves. In other words, how fast the oscillations were. Now, it turns out that if you know the wavelength and the frequency, you know the speed. Because the speed of a wave, it was well known since Newton's day, that the speed of a wave is equal to the wavelength multiplied by the frequency. Now, when Hertz did this calculation, well, he found that, for example, let's say he's got a wavelength of 1 meter. And he finds that he's got a frequency of 300 million cycles per second. And lo and behold, that gives you a speed of the wave of 300,000 kilometers per second, which is 186,000 miles per second. So he was actually able to compute, based on measuring the wavelength and the frequency of these electromagnetic waves that he generated in his lab, he was able to compute the speed, and he gets the exact same number that had been measured for light before and had been calculated by Maxwell. Troy, did you have a? Okay. So, again, we come back to this same magic number. So he's proven now that these waves that he's generated go at the same speed as light does. So they're transverse waves just like light. They can be polarized just like light. they travel at the same speed as light, they reflect the same way as light, they refract the same way as light, they are light. Pretty strong argument. Now, the one thing Hertz missed in this was one of his students that was working for him as a research assistant. After he did these experiments and discovered this, they asked him, well, what's the importance of this? And the only thing Hertz could think to say was, well, it proves Maxwell's theory. You know, I mean, it proves Maxwell was right about electricity and magnetism. Not only are Maxwell's equations right, but it also proves, it gave a really strong argument for the first time of the real existence of these electric and magnetic fields. You know, we can't see these things. Now, Faraday was the first one to start thinking in terms of these crazy lines in space and these electric and magnetic fields. But of course, the only things we see are magnets and wires, and so people weren't sure whether to believe Faraday. Well, I mean, after Hertz does his experiments showing, proving the existence of these electromagnetic waves, well, then you have to think in terms of electric and magnetic fields. So Hertz thought of this as a great confirmation of the physics of Faraday and Maxwell, and in particular Maxwell's idea that light had to be electromagnetic waves. But other than that, he couldn't really think of, you know, what good this discovery was. Well, it didn't take other people very long to figure out that this had fantastic implications. It was only a few years after this that people started building radios. And within a dozen years after these experiments were published by Hertz, people were building radio transmitters that in England that could send signals all the way to the United States. And then within 20 years after that, by the 1920s, people could not only send simple little Morse code signals, but they could send actual voice transmissions through the air for thousands of miles. So it started a whole technology boom. This incredible discovery that now unfortunately Hertz didn't live to see that. He died shortly after he made this discovery, and so he never heard what it led to. But obviously radio, television, satellite communication, all of that is based on the kinds of waves that Hertz generated. Those are electromagnetic waves, but of this long wavelength type that is referred to as radio waves. Now, so if we think of light now, once we have these discoveries, people started figuring out that light is just a particular type of electromagnetic wave. That if let's say you can call this section electromagnetic spectrum. Okay, like we had a color spectrum, okay, which was made up of different wavelengths of visible light. Okay, but that's only a very small portion of the total spectrum. What Newton saw through, when he spread white light out through his prism into the various colors. Newton saw a little section of this electromagnetic spectrum where, let's say you have red here, blue here, and this is, all visible light is within those extremes there, and all those wavelengths are about a little less than a millionth of a meter, right? So it's actually about a half of a millionth of a meter. Now, the way over, if you keep going to longer and longer wavelengths, past red, okay, now we covered infrared, right? So you have infrared light here, which is longer wavelength. Then you have, people would discover what are now called microwaves, and then radio waves. And radio waves are on the order of, well, for AM radio, you have waves with wavelengths of, bigger than football fields. Long, wavelengths of a few hundred meters. For FM radio and television, you have wavelengths that are more like 1 meter. So you can now, what about the other short wavelength?
Ultraviolet.
Yeah, you have ultraviolet out here. Now, do you know of anything else out here? You've all heard of X-rays, right? The dentist and the doctor have all they've shot these things through you. Now, they're really very short wavelength and high energy. So that's why they usually like to cover you up with a lead jacket or something. Oh, I'm going over, aren't I? Okay, and then the last thing there's even something called gamma rays out here that are even shorter. So you have this whole continuous spectrum, and I'll tell you a little bit more about it next time and the technology that comes from that.